Hi students, in our previous video we had discussed about the extraction of iron from the blast furnace. There we had used different ores, hematite and the magnetite, and we related the so-called extraction of iron with Ellingham diagram. Now our concept is extraction of copper from cuprous 1 oxide. So in this video we are going to discuss how to extract the copper from the cuprous 1 oxide. Remember the point, whenever the oxidation number we have of the particular metal, it is represented in the capital Roman number in a simple bracket. Observe cuprous 1 oxide means copper oxidation state is +1, oxygen we know 2 minus 1 into crisscrossing. What will be its formula? Its formula will be Cu2O, cuprous 1 oxide. The compound formula will be Cu2O. But the main point here we need to observe is copper ore is not obtained in oxide form. It is in a mixed form with sulfur. It is in a mixed form with sulfur. What is the ore of copper? Ore of copper means we are having the word chalcopyrite. What is the word? Chalcopyrite. Here CuFeS2. CuFeS2. The word of copper pyrite. We can call this as copper pyrite. Copper is not obtained in a individual form. It is obtained in the combined form. Here it is having iron also along with sulfur. Now we need to separate our copper from the mixture with iron. So the first thing is we must heat this ore in the presence of oxygen. In the presence of oxygen. Here we are going to decompose this ore. The first thing what we are going to do is we are going to decompose this ore. The decomposition of this ore is done in a river battery furnace. In river battery furnace. In river battery furnace. In river battery furnace. Ore is decomposed. What will be done here? Ore is decomposed by the process of roasting. By the process of roasting means we supply the oxygen. We supply the oxygen. Observe CuFeS2, the copper pyrite we can call. It is heated. Roasting means heating in the presence of oxygen. In the presence of oxygen. Where are we heating this ore? We are heating this ore in a river battery furnace. CuFeS2 upon heating with oxygen, this is going to decompose to form Cu2S plus Fes and also one byproduct. We can observe what will be the byproduct after knowing the balancing of the reaction. We are using 2 moles to balance the products. So how many coppers you find here? 2 coppers you find. These 2 coppers will be taking up 1 sulfur to form Cu2S. Now can you put say this is cuprous 1 sulfide. What do you call this as the cuprous 1 sulfide? I had already explained cuprous 1 oxide means Cu plus 1 O2 minus. Sulfur also will be having 2 minus. In this case 2s are 4 in the reactant. We have used up 1 sulfur. Now observe, 2 of the irons are reacting with 2 of the sulfurs to form iron sulfide. They are forming the iron sulfide. Now we have used 3 sulfurs up to now. The remaining 1 sulfur will react with oxygen and will be escaped in the form of the oxygen gas. So the first thing, what have we done for this ore? This ore is fed into a river battery furnace for the decomposition purpose. Along in decomposition, we had done the process of roasting that we had done in the presence of oxygen. Here we are having an impurity present in this ore. We are having an impurity present in this ore. What is the impurity present in this ore? Means impurity in the ore of copper is FeO. What is the impurity here? FeO. Iron oxide is present as the impurity. In this ore, iron oxide is present as the impurity. So, in order to remove this iron oxide in the form of slag with some other component, we are adding some other component as the silica. Silica is added as flux to slag of FeO as FeSiO3. The iron silica slag. What do we call as the iron silica slag? Iron silica slag. The substance that we are adding to remove the impurity, we call it as the flux. What do we call as the flux? So what is the flux added here? Silica is added as the flux to slag off, means to remove the impurity in a combined state. The impurity FeO, when it is going to react with this so-called added silica, what is the formula of silica we know? SiO2. The formula of silica is SiO2. We can see this reaction here. The impurity FeO, when added by SiO2, it will form FeSiO3. It is removed in the form of molten slag. So we had observed this point. What is the ore of copper we call, and how to do the decomposition process, and also the impurity present in this ore. Now we got in the decomposition 2 main components. One is called cuprous sulfide and another one is called as the iron sulfide. This cuprous sulfide need to be converted into cuprous oxide. Cuprous sulfide need to be converted into cuprous oxide, because when we went through the Yellingham diagram the day before class, the delta G negative versus temperature, the formation of cuprous oxide, when you observe, 4Cu plus O2 gives rise to 2Cu to O2. It got at the top of the remaining lines. What are the remaining lines? Formation of carbon dioxide from coal, formation of carbon monoxide from coal. We came to know when the delta G negative value of a metal oxide is at the top and the remaining lines are at below, these can reduce the metal oxide. The lower lines can reduce the metal oxide that is present get the higher delta G negative value. Keep in mind, the higher delta G negative value is reduced by negative, more negative delta G negative value. Here Cu2O is at the top and the remaining carbon monoxide line is at bottom, carbon dioxide line is at bottom when compared with this one, and the CO is also at the bottom when compared with this line. So we can use the coke or we can use the carbon monoxide as a reducing reagent to reduce the copper oxide. But we cannot reduce the copper sulfide directly into the metallic copper. Hence, we need to convert our copper sulfide into copper oxide. Then we need to add our reducing reagents like coke or carbon monoxide. So what is that? Another application for Willingham diagram? Another application for Willingham diagram is to understand that copper oxide will be reduced by coke or carbon monoxide. So let us continue in converting the cuprous sulfide into cuprous oxide. We had observed in the previous decomposition reaction of the copper pyrite that it forms Cu2S and Fe(S). Now the Cu2S along with the Fe2S, Cu2S along with the Fes, these both are fed into reverberatory furnace that is lined with silica. There the roasting takes place. Roasting of the reactants. What are the reactants here now? Cu2S and Fes. This Cu2S that is formed there when it is undergoing the process of roasting. Roasting means heating in the presence of oxygen. See, Cu2S when heated in the presence of oxygen, it is going to form Cu2O. What is it going to form? Cu2O. And it is also going to form sulfur dioxide gas. For the purpose of balancing, we are bringing 2 moles of Cu2S. 2 moles of Cu2S. We can observe here like how many moles we have totally? 2 moles of copper sulfide. So it is going to form 2 moles of copper oxide. There are 2 sulfurs here. In the products also we are having 2 sulfurs. You can balance the oxygen slide. 3 2s are 6. In the products we had 2 oxygens here and 4 oxygens. So during roasting, copper sulfide is converted into copper oxide. Copper sulfide is converted into copper oxide. And also, what happens for Fes? The Fes, remember this point very clearly, Fes will also undergo the process of roasting. During roasting, it is converted as FeO plus SO2. FeO plus SO2. Now can you say this FeO is still present as the impurity. Fes during the process of roasting is supply oxygen. Using that oxygen, this Fes is now converted to FeO. This FeO in the starting we had removed, which is present along with 4. Now this is the FeO form from the Fes. That is the copper pyrite along with the composition we had. Fes is now oxidized to FeO. In order to remove this FeO, we are adding the silica the refractory furnace in excess. So this excess of silica will remove the iron oxide in the form of iron silica slab. In the form of iron silica slab. So we call this one as a flux. Silica flux we can call. For the balancing we are adding 2 moles and we can get this one also as the 2 moles. Means whatever is produced, iron oxide is produced by the addition of excess of silica, we are removing that iron oxide in the form of silica slab from the composition. This step you don't get confused. Starting we had removed no sir. We had removed the iron oxide that is present along with coal. Now this is formed due to the roasting of the Cu2s and Fe(S). This composition of Cu2s and Fe(S), Cu2s and Fe(S), that is present in the starting. It was questioned in many of the objective questions. What is this composition known as? This composition is known as copper meal. Is known as, what is this known as? Copper meal. The copper sulfide present along with iron sulfide is called as the copper meal. Very important 1 mark question as well as the objective question. Copper meal is the composition of Cu2s and Fe(S). This Fe(S) went on for roasting and it was removed by the excess of silica added into the refractory furnace. So up to now we had converted our copper sulfide into copper oxide. Now how to get our copper? We explained that this so-called coke or carbon monoxide can be used. Coke or carbon monoxide can be used. But here the reaction goes like an self-redox reaction. Like an self-redox reaction. What is like a self-redox reaction? The reactant Cu2s a little amount of Cu2s is left behind unreacted. Little amount of Cu2s is left behind unreacted. It will be reacting with the Cu2O formed in the course of reaction. Please observe how many coppers we got in this molecule. 2 coppers we got. Here we have totally 4 coppers. These coppers are converted into metallic copper. From both of the reactants, copper is separated. And sulfur will undergo oxidation but for the formation of sulfur dioxide gas. These both are in the reactants only. What are they undergoing? Cu2O is undergoing reduction and Cu2s is undergoing oxidation. So in a reaction when both reactants are participating in reduction and oxidation, what do we call this type of reaction? We call this one as an redox reaction. What do we call this one as an redox reaction? We call this one as the redox reaction. So we have obtained the copper, metallic copper, by the reduction of copper oxide by using the same reactant left behind unreacted Cu2s, which is acting as a reducing agent here, and itself is undergoing oxidation, because sulfur is going to gain the oxygen. So this is the process of obtaining copper from the copper ore. Now we have a last topic left over, how to get zinc metal from zinc oxide. How to get zinc metal from the zinc oxide. Let us continue with it. Let us see the next example. Extraction of zinc from zinc oxide. This zinc oxide, when reacted with coke at a very high temperature, above 1673 Kelvin, above 1673 Kelvin. At that temperature, at a very high temperature, when it is reacted by coke, the zinc oxide will undergo reduction to form metallic zinc. So we can speak coke is acting as an reducing agent in this reaction. A very simple and direct equation. In the Ellingham diagram, when we compare, the zinc oxide line is about to the coke. Hence coke, which is having a more negative Gibbs free energy, can act as a strong reducing agent to reduce the zinc oxide. So zinc oxide on reduction with coke reduces to metallic zinc. These are the reactions that we have discussed up to now about using thermochemistry principles. Thermodynamic principles we can call. These are all involved in applying heat. These are all involved in applying heat. So these topics are concluded here, and next class we shall discuss the electrochemical principles in the extraction of metals from the ores.